Here's where we evaluate the possibility of using lightweight materials wherever we can. Aluminum, plastic, high-strength steels. All are considered and evaluated and tested. This is also the time when we begin to hand build every part of the body, down to door handles, locks, and window mechanisms. All must work properly and fit together right. This is where we can quickly refine the body surface dimensions exactly the way we want them to be built. We work right at the computer console with the mathematical model of the body. We call this process sweetening, smoothing out the curves so they'll be truly functional and at the same time pleasing to the customer's eye. By the time all the final contours of the body have been determined, the computer contains a master mathematical model of the body shape with precise dimensions. Fisher Body Engineering can use the computer to make master drawings of any component, to any scale, even perspective views. It can be used to control cutting tools that shape wood models of body segments. Letting a machine do the rough shaping gives the model maker a head start, leaving the fine detail work to his irreplaceable human touch. Then by placing these wood models together in what is called a cube-up, engineers can easily check how they fit together before actual parts are produced. But it is in the basic performance evaluation of the body structure where the innovators from Fisher Body have made the computer an especially invaluable tool. It permits them to conduct comprehensive design test programs long before any actual prototype bodies are built. Using a technique called finite element modeling, they can predict ahead of time the stresses on various parts of the body structure under specific static or dynamic conditions. With finite element modeling, we can actually see what happens to the body structure when the car travels over bumps and rough terrain. We can even simulate what might happen to an occupant of the car in a crash. This information helps us design lighter weight parts that do the job. Innovative use of the computer at the engineering design stage has helped tell Fisher engineers where to take hundreds of unneeded pounds out of modern automobile bodies. And in a number of instances, reliability has been increased by simplifying design and reducing the number of parts. With the finite element modeling input to work with, the first physical model of the body is built in plastic, exactly 1/2 the size of the full-scale car. This model is used to learn even more about the structural performance of the new lighter weight body. How much will the body bend when the vehicle is jacked up? We can tell almost exactly from the reaction of the plastic model. How does the body withstand road vibration? A strobe light set to the frequency of the test vibration acts to slow down the motion so the body's reaction becomes visible. If the deflection is too great, a joint may be redesigned or an area of the body may be braced or stiffened. Then the test is repeated. Plastic models, when covered with a special coating, show where strains and stresses appear during simulated driving tests. Actual proving ground data are entered into the test equipment so the results can be correlated to actual driving experience. Then, still another model is built, a half-scale steel model. Models like this are used to test performance. And then, they are even tested to destruction. This Fisher Body Engineering film shows the remarkable similarity between the test results of the half-scale model with those of a full-scale prototype body. Tests like these, early in the body development, save 90% of the cost of testing if full-size prototypes were used. But as important as the finite element and model testing are, they still cannot totally replace the need for building full-scale prototype bodies by hand and subjecting them to a rugged evaluation program in some of the most elaborate laboratory test facilities in the world. Only in this way can the Fisher body engineers be sure that every part fits together the way it has been designed to fit and does the job it was designed to do. Quality, durability, and reliability. These are the goals of all this laboratory testing. Will the body stand up to sub-zero cold? Is it tight enough to keep out the finest of dust? Will the windshield wiper work the way it's supposed to as long as it's supposed to? What about the doors? Will they open and close the specified number of times without fault? How do special corrosion-resistant metals react to constant dousings with salt water spray? How about a new seat fabric? Will it stand up to the prescribed amount of wear? What about seat belts? Do they retract the way they're supposed to? Do the electric windows operate smoothly? How about the power seats? Electric door locks? Trunk lid releases? Do all the parts fit together the way the designers intended them to? As comprehensive as these tests are, they cannot answer all the questions that must be asked. It takes actual driving to do that. So the innovators from Fisher Body subject every new car body design to driving tests under carefully controlled test procedures at the extraordinary facilities of the General Motors Proving Grounds in the hills of Michigan and in the desert of Arizona. The hand-built models undergo programmed durability runs that compress thousands of miles of average driving into a few weeks. They are tested for their quietness and for their resistance to corrosion. They are bruised, beaten, battered. It is still months before the new body is scheduled for mass production. Still time for any necessary changes that will improve the quality, the durability, or the safety of the body. While testing goes on, process engineers have been completing the design of the tools and dies necessary to mass produce the body. We build pilot lines right here at Fisher Body, so tooling can be checked out before it is installed in the plants. And then, actual lead unit models are scheduled onto the actual production lines with current year cars to check the entire assembly process under plant conditions. Finally, everything is ready. 2 years have passed since the clay model was approved. The goal of the project team has been achieved, and the new General Motors car is ready for production. Lighter weight, more economical to operate, and possessing all the qualities that the consumer demands. Production schedules arrive at all Fisher Body plants and other GM facilities. The complex manufacturing process is about to get underway. There are about 3,000 parts in a typical Fisher Body model, with as many as 115 different models built in a single year for the 5 GM car divisions: Chevrolet, Pontiac, Oldsmobile, Buick, and Cadillac. So hundreds of thousands of different parts are built every year, with an equal number purchased from thousands of suppliers. And the miracle of the modern automobile is that everything ends up at the right place at the right time. Attention to quality. That's the major charge of the production team in every one of Fisher Body's 11 metal fabricating plants. And in the 5 trim fabrication plants. In the trim plants, a Fisher body manufacturing innovation is clearly in evidence. Thick layers of upholstery fabric cut automatically, accurately, efficiently by machines controlled by computer-generated tape. But in trim plans like this, it is the personal touch that is most in evidence. Experienced seamstresses stitch seat coverings and door trim and headliners. Machinery helps where it can, as in the vacuum forming of vinyl shapes, or the fabrication of door panels. But always the human touch is there. People who know what they like in their own automobiles work to make every interior appointment as close to perfection as possible. There is one place in the trim fabrication plants where automation takes over. Tape-controlled stitchers do delicate embroidery in minutes without flaw. The same job would take many, many hours by hand. Quality is also the way of life in Fisher's 6 hardware fabrication plants. Here, an almost infinite variety of components are fabricated. Parts that are important both to the function and the appearance of the automobile body. They include new lightweight window regulators, door handles, door and trunk hinges, locks, moldings, one-piece roof liners, even seatbelt retractor assemblies. The hardware plant is a busy place, and the teamwork between people and machines is especially evident. In each of Fisher's fabricating plants, a continuous test program checks on the quality of the manufactured parts. We have an array of laboratory test facilities to cycle, bend, cut, pull, flex, rub, bake, freeze, and measure production parts. If any of them fail to meet spec, we take corrective action immediately. Only acceptable components are approved for assembly. There are a number of plants where Fisher bodies are assembled. Quality is the byword here, too. Welding is a key to structural soundness, and at Fisher, great care is taken to assure that every weld is the high quality the body integrity demands. The pace of the assembly line is steady. And then, final metal inspection. Here's where the results of all that early body structure development shows up. The surface is fit. The contours flow smoothly. The body that began as designer's clay has emerged in hard steel. The assembly line continues on, and the painting process begins. Here's an example of where innovation is at work in the production process. Each body is primed, many by dipping them into an electrically charged corrosion-resistant bath we call cathodic ELPO. The primer bonds onto the metal like iron filings to a magnet. Every crevice and corner are coated. This is an important part of a major Fisher effort to prevent corrosion. After baking on the primer, the rust-prone areas of each body receive still more corrosion resistance. a wax coating first, then a plastisol sealer to protect critical joints, then baking, wet sanding, and primer sealing. And finally, the exterior finish is applied. The whole paint sequence is handled by computer. Sprayers change colors automatically, depending on the program schedule. And the long-lasting paint is applied evenly, smoothly. The bodies continue without interruption. The conveyor line is laid out so any flaws or defects can be corrected without taking a body out of sequence. This is important because somewhere in another part of the assembly plant, seats and trim of just the right color are heading for a rendezvous with this particular body. It all works out exactly as planned. And then the water tunnel. Every Fisher body is drenched from all angles to check for water tightness. Any necessary corrections are made before the body moves on. More trim is added. The one-piece roof liner is snapped in place. Door pads are installed. Finally, the seats move into place. And here is where the miracle of manufacturing scheduling is apparent. The right color seat is right there alongside the right color body. When the seats go in, assembly is completed. Release to the car division. Fisher body's job is done. The line moves on, in some cases right into an adjoining final assembly area. In others, they are transported to nearby car division plants. Then the body is moved into position to be united with the automobile's chassis. Its wheels, engine, transmission, brakes, steering, they all await the body by Fisher. And so another General Motors car is on its way to completion. A beautiful object indeed, destined to provide excellent personal transportation for a proud and discerning buyer. But more than all that, it is also a magnificent engineering achievement. The challenge has been great. The investment has been considerable. But the results have been achieved. This is a tribute in no small way to the creativity and ingenuity of the innovators from Fisher Body.